Thank you very much for inviting me. As you mentioned, I did my PhD in Australia a number of years ago under supervision of Professor Martin Savesberg and Natasha Bullen in the University of Newcastle. I guess some of you may know them. And since then, I have been always trying to stay in touch with my Australian friends and colleagues and get involved in any research activities whenever I have time. And so when I got invited to this seminar series, I happily accepted to be part of it. And right now it's 2 a.m. here in Florida, but so hopefully I'm not very tired to explain and discuss about my research. So today I'm going to talk about a class of optimization problems that I have been working on that for a few years now. And so specifically, I'm going to talk about an issue that we faced when solving a real-world optimization problem, and we named that issue the curse of multiplication. And that issue was basically bothering us for a few years. And finally, we were able to develop a new family of solution methods for resolving that issue. So I have a long list of collaborators. And so here is just like 3 of them, Payman and Vahid. They are more former PhD students. Fabian was my classmate back in Australia. So we were office mate and we were doing PhD together in Australia. And since then we have been always in touch. And one other thing that I wanted to mention, although the title of this seminar series is artificial intelligence-based optimization methods, my talk will be mainly on the side of basically traditional optimization. So with that in mind, since my main area of research and expertise is basically multi-objective optimization, I would like to start my talk by telling you a little bit about multi-objective optimization and how did I get to work on the class of optimization problem that I want to talk about. So how did I get there from multi-objective optimization to that class? Hopefully this path would be interesting enough and I would be able to convince you that this class of optimization problem is actually interesting to work on. So basically, whenever we are talking about multi-objective optimization, we are dealing with P objective functions. These objective functions, let's call them y1x to yp of x. And these objective functions are typically conflicting, and we're trying to optimize them, basically maximize or minimize them over a given feasible set. So whenever we have a multi-objective optimization, we are interested in finding the set of efficient solutions of this problem, denoted by Cali XE here. And these are basically the solutions that that is impossible to improve the value of one of the objective function without making the value of at least one other objective worse. So just as an example, if we have, let's say, 2 objective functions that we want to maximize, let's map every single feasible solution into the space of objective functions. And in that case, we're going to get a picture like this. And as you can see in this picture, there are some points that are highlighted by blue. So these are basically the image of efficient solutions in the criterion space. So these are the points that we are actually interested in. And the red points are actually the points that are dominated. They are not representing any efficient solution. So the reason that these red points are not representing any efficient solution is because, for example, if you consider these 3 red points, all of them are actually dominated by this blue point. So that means that this blue point has a better objective values. So whenever we have multi-object optimization, we are interested in finding these sort of efficient solutions, or this what they call as a Pareto optimal solutions. In multi-object optimization, there's also a direction of research. It's called optimization over the efficient set, that I have been working on that for a number of years. So it basically says that what happens if we don't want to try to optimize, try to find all the efficient solution. We basically try to optimize a function over a set of efficient solutions. Okay, so I'm going to explain that thing about it a little bit more in a minute. But this sort of research direction exists in the literature. And so when I was working on this research direction, I started to ask this question, whether or not this research direction has any intersection with the single objective optimization direction. So that basically means that whether or not there are any problems in the that you can actually solve them both from the angle of single objective optimization or from the angle of the optimization over the efficiency. Okay, so remember, when you're dealing with a single objective optimization, you're trying to optimize a function over the set of all feasible solutions. And when you're solving an optimization over the efficient set, you're trying to optimize a function over the set of all efficient solutions, right? So basically, these two in the intersection section, these two definitions should be the same thing, should match with each other. So that means that it doesn't matter whether or not you're searching over the entire feasible set or the set of efficient solution. Both of them will give you the optimal objective value. So I started to ask this question, and it turns out there are several class of problems that actually lie in this intersection. And one of which I'm gonna talk about today. Just to provide more explanation about the optimization over the efficient set, this is an approach that you try to find the preferred solution among the set of efficient solution. Normally there is a function representing how decision maker will choose their preferred solutions from the set of efficient solutions. And all you need to do is to maximize that function g of x over the set of efficient solutions of the problem. Okay, so that's all you try to do. And now I'm going to talk about that class of optimization problem that lies in the intersection of optimization over the efficient set and multi-object and single object optimization. So that means that it doesn't matter whether or not you are solving if you're optimizing g of x over the set of efficient solution x of e or the all feasible solutions. So here's a
hi Hadi, I have a question.
Sure.
So given the set X, so that was your original domain of solutions over which you want to optimize, right?
Yes.
So, and then you are saying that I want to now optimize over this set XC, which is the set of efficient solutions.
Yes.
So given X, how tough, how complex or hard is it to compute this efficient set? It doesn't seem to be a trivial problem, right?
No, it's not. So in the optimization over the efficient set, we do not try to enumerate all efficient solutions and then optimize. We try to optimize it directly. So that means that we find 2 or 3 efficient solutions. And once we find these 2 or 3 efficient solutions, we can safely say that, for example, we found the optimal solution. So you search.
You are given this set XC, or you are given literally the set X?
No, the XA is not given. It's not given. So you need to calculate some components of that, not necessarily all of them.
Is it specified in some kind of implicitly?
Yeah. So no. So you only have access to entire feasible solutions. But the set of constraints defines your feasible solution. So that's all you have. Okay. So let
Okay.
me, for example, explain to you in what the problem that I'm actually working on, and that will hopefully make it more clear. Okay. So this is a multiplicative program, the problem that I actually want to talk about it today. So you're trying to maximize or minimize a multiplication of some non-negative functions. Okay. So these are functions that are non-negative over all feasible solutions. Okay. So it turns out that if you want to solve this problem, this is obviously single objective optimization, but at the same time, this problem is equivalent to solving this optimization over the efficient set problem. So you're trying to maximize or minimize the same function over the set of efficient solutions, right? So that means that your multi-objective optimization is maximizing or minimizing y of y1 of x to yp of x. If you know the efficient solution of this problem, if you optimize this product over the efficient solution, it gives you the same answer as the single objective optimization problem mentioned above. So these two problems are equivalent. Okay. So now you can develop an algorithm for solving this problem from the angle of single objective optimization, or you can develop an algorithm for it from the angle of multi-objective optimization. And I have been doing that for a number of years now. So we have a few algorithms developed for this class of optimization from the angle of multi-objective optimization, and they work pretty well for small values of p. And then you can also develop some algorithms or use the state-of-the-art techniques for solving this class of optimization problem from the angle of single objective optimization. So let's talk about some applications of this problem. Well, this is the application that I have been actually working on with my partners in the United States Geological Survey. So whenever you're talking with a conservation planning scientists, the goal is to preserve or maintain biodiversity. One of the problems that they actually try to solve is, for example, knowing which sites or parcels should they protect within a geographical region in order to preserve biodiversity. So they have a bunch of parcels. They define one, they introduce one in binary decision variable for each parcel. And then this decision variable basically shows whether or not you want to purchase that parcel or you don't want to purchase that parcel. And you have a bunch of constraints as well. You want these selected number of parcels to be, for example, connected to form a compact shape. So you can have lots of constraints if you like. So now the main issue is that preserving biodiversity is a vague goal. So what does it mean to preserve biodiversity? So one typical challenge is to basically define this goal. And there are multiple ways. One of the ways to define this preserving biodiversity is through multiplicative programming. So you're trying to maximize this multiplicative function. So you have 1 minus fi of x. Fi of x is basically the extinction probability of a species I. So you have p species. And what you try to do is to basically maximize the survival probabilities of all the species together. So you try to save as many species as possible. And you can also solve a minimization form of this problem if you're interested in just basically solving not necessarily all of the species, but just at least one of them. So you try to minimize the product of their extinction probabilities. So you can solve any of them if you like. So another application.
So I have a quick question. So in this, you are implicitly assuming that the extinction or the survival probability of each, so they are like mutually independent, right? So
Yes.
is that a realistic assumption?
Yeah. So in many of the applications that we have been working, so it was basically hard to detect whether or not they are actually not sort of independent. So in many of the applications that I've been working, the conservation planning scientists, they assume that's the case. Okay. So I personally don't think that that's necessarily represent the nature, but that is mostly what they do. So here we have an application, another application that I think is actually quite interesting. It's in the context of game theory. So there's a class optimization problem called bargaining problem. Bargaining problem is basically a cooperative game in which all players agree to create a grand coalition instead of competing with each other in order to get a higher payoff. So they don't want to compete. They just want to, they are independent players that they want to cooperate in order to get a higher payoff. So one of the solution proposed for this for calculating. So basically in this domain, the main question is that what should be the payoff of each player in such a grand coalition? And one of the solutions proposed to solve this problem is basically multiplicative program, which is proposed by Nash in 1950. So and the Nash named this thing as a nice social welfare. So this is a nice social welfare function. So you're trying to maximize the product of benefits of the players, so benefits that they obtain from such an agreement. Okay. So here's my just a personal view that I wanted to share. I have a talk about it. If you're interested, you can just listen to that or look at the references. So there are several problems that that I have been facing over the last few years, that they normally have a large number of objective functions, and so because they have a large number of objective functions, it's very hard to calculate the entire non-dominated frontier or efficient frontier. In such a problems, I found it typically convincing or typically good if you do not solve the multi-objective optimization, you just solve its multiplicative programming counterpart of the multi-objective optimization. So that is, if you have that basically means that if you have, for the functions that you are trying to maximize, you find the upper bound, and for the functions that you're trying to minimize, you find the lower bound, and you try to maximize this function. And so that normally gives you one of the solutions that are actually interesting. These WIs here are actually the weights. And these weights, you can select them any desirable weights that you like, or you can make them equal to 1 if you want. So, but that is basically a multiplicative program that you can deal with. Yeah. So if you like, you can now also listen to this talk. So now let me tell you a little bit about what. So we're not going to look at all multiplicative programs in this talk. We're just going to work on mixed integer linear multiplicative programs. And basically, any mixed integer linear program, mixed integer linear multiplicative programs can be written in this form. In the mixed integer linear multiplicative programs, all the constraints are linear. So the only non-linearity term comes from the objective function, and we have a bunch of continuous and integer decision variables. So for simplicity, from now on, I'm going to represent this mixed integer linear multiplicative programs using this thing here. So although you can develop algorithms for this problem from both the angle of optimization over the frontier or single objective optimization, for the issue that I'm going to mention, we were not able yet to find an algorithm optimization, a sort of multi-objective optimization based algorithm, but we were able to find a new family of solution methods from the angle of single objective optimization. So my talk will be mainly on this domain from now on. So because my talk is going to be mainly from the angle of single objective optimization, I first need to tell you how we can actually solve a mixed integer linear multiplicative program using single objective optimization techniques that are out there. So if you're solving a maximization case, or maximization form, a typical approach for solving this problem is to change the problem into a logarithmic form. So you apply a log transformation to the objective function. And that's because as I mentioned, yi's are actually all non-negative. So you just apply, and this is a concave function. So therefore, you can use a log transformation. Remains so the function remains concave. So now you can pass this thing into any sort of mixed integer convex programming solver, and they should be able to solve the problem. The second approach, if you don't like sort of the log function or non-linearity function, you can try to linearize the log function, especially if you have if yi's are integers, if yi's are integers taking value from the domain of li to ui, you can enumerate all those values and put them into the log function. You calculate the log function in advance, and then you can define a one binary variable for each log values. And then in that case, you can linearize the log function. So once you linearize it, you can actually pass it to a integer linear programming solver to solve the problem. My favorite approach for the maximization case, it's a second order co-programming transformation. Basically says that if you have a problem of like this, a multiplicative program, that is equivalent to solving this geometric mean optimization problem. And there's a nice way to change any geometric mean optimization problem into a second order programming problem. In our case, this is going to be a mixed integer second order programming. So we use the Benthal and Nemirovsky transformation, and that will change the problem into a second order program. And so the nice thing about mixed integer second order programming formulations is that you can actually solve them using Groby or Cplex. Okay, so you can use their powers to solve the problem very, very efficiently. So I'm not going to go through the details, but if you like, you just can go to the paper of Benthal and Nemirovsky to learn about this transformation. So how to solve the minimum case? So for the minimum case, the issue we have there are lots of issues. So minimum multiplicative programs are actually very tough to solve. Even if you don't have any integer decision variable, the problem is going to be NP hard. And so there are not many approaches out there from the angle of single objective optimization that can solve the problem. So one way, a simple way, is to pass the problem as is to a global optimization solver to solve the problem. Another approach that is sort of, I would call it more recent, is to use a Groby non-convex sort of quadratic solver. So that basically means that when you are multiplying three components together, y1 multiplied by y2 multiplied by y3, you can actually apply a sort of a nested sort of multiplication. And once you apply the nested multiplication, you only have quadratic terms, and now you can pass this to a non-convex quadratic solver of Groby to solve the problem. Okay, so now let's talk about the Kershaw multiplication. So when we were working on this problem, we were developing different algorithms for this class of optimization problems. We realized that when the P is large, so when you have a large number of terms in your objective functions, you will face some numerical issues. And for example, if the yi values or the factors are in the domain of 0 to 1 or 1 to infinity, then these numerical issues can arise quickly when P is large. If you look at this example, we have P equal to 100 and assume that all the y values are 99, an optimal solution. So that means that your optimal objective value is going to be 99 to the power of 100. So which is a very, very large number to handle. So no wonder that when you're solving this problem, you face numerical issues. So transformation-based techniques also, they face some other sources of numerical issues. For example, the problem that they have is that this type of transformation, they also make the value of the sort of a function irrational, and irrationality makes other sources of numerical instabilities. And normally these algorithms, they cannot claim that they found an optimal solution, right? So um, because they make the value irrational value. So anyway, so if you pass a problem with a large value of p into existing sort of techniques to solve the problem from multiplication problem, you face a numerical issue. And that was bothering us, and we call that issue a curse of multiplication. And we were trying to solve that issue since then. And so we came up with an idea. Our idea was to basically binary encode the multiplication operation, similar to how a computer conducts it sort of internally. So that's the idea that came up to our mind. So basically, our idea is to use the fast Fourier transform based multiplication of integer, so which is closely related to the ancient way of conducting multiplication that has roots back in around 1500 BC. And I'm sure that you're all familiar with that type of multiplication. So here's just an example. If you're trying to multiply 14 by 5, you can transform 14 into you can write the binary encoded version of 14, which is going to be 1110. And then you can write the binary encoded version of 5, which is going to be 101. And now you can multiply them together using this fast Fourier transform-based multiplication of integers. So each of these terms in the middle here are multiplication of two binary values. So for example, 0 here is the multiplication of 1 and 0. Once you do that, then you need to calculate the sum of each column represented by V here. And you have some carried values here. So that those are the values that goes from one column to the next column. So we represent the carried values by a notation of C. And finally, once you have the summation, once you have the V values and C values, you can add them together in order to calculate your final multiplication value, which is represented by Z hat here. So y1 multiplied by y2, it's going to give you the value of 70, and the binary encoded version of the 70 is whatever that we wrote there, is 1000110. So we basically want to apply the same principles in order to write down a binary encoded version of the multiplication that we have. So what does that mean? So I'm going to explain that using a simple example. And so in this simple example, I'm assuming that we have two values, only two values, y1 and y2, and I'm going to multiply them together. So let's see how we can do that. And so more importantly, I assume that these y1 and y2 are integer. At the end of my talk, I'm going to tell you what to do if they are not integers. And then these values are going to be less than or equal to 10 for now. So the first thing that you need to do is to find an upper bound for your optimal objective value. This can be done easily because you have an upper bound for your y1 and y2. So you just multiply them together, giving you the value of 100. And then you know that 100 is the largest value that you can get. So that means that at most you're going to have 7 bits to represent, to binary encode your objective value. So you have only 7 bits. These are denoted by z hat 0 to z hat 6. So I find the number of bits that I need. And then first, in the next step, what I'm going to do is that I'm going to binary encode y1 and y2 because I'm going to multiply them together. So you write linear equations to do the job. So this is the binary encoded version of y1. This is the binary encoded version of y2. Then what we're going to do is that we're going to apply the principles of binary multiplication. We apply the principles of a binary multiplication, the fast Fourier based transformation that I explained earlier. So basically, you need to calculate the V values. If you remember, V values was the sum of each column, and sum of each column was basically the sum of binary multiplication that you had. So This is the equation, and this equation is nonlinear. It's actually sum of some bilinear terms. Then you need to calculate the carried values. In order to calculate the carried value, you can use this equation. So a carried value from column J to column J plus 1. You carried value from a column J minus 1 to column J. You use this equation. It depends what was the summation of the previous column and what was the carried values to the previous column. So if you add them together, divided by 2, round it down, that will give you the carried value for the next column. So this is also a nonlinear equation to deal with. And the last thing, once we found the Vj and Cj, we can add them together. And you can also use this set of equations that I write here to calculate the z hat of g. And this is a linear equation. So, and these are simple equations. Actually, you can check them by yourself, and you realize that these are precisely representing the binary multiplication platform that I mentioned previously. So basically, now we have 4 types of equation. Equation number 1 and 4 were linear, but equation number 2 and 3 were nonlinear. So now, in order to write down the binary encoded reformulation, we need to put all these pieces together. So the binary encoded reformulation of the multiplication program is nothing but this one that I have written up for you here. You are trying to maximize and minimize this binary encoded version of your objective function. And you have some new variables. Y hats are some of them, carried values and the sum of the columns. And z hat is basically the binary encoded, the bits of your optimal objective value, basically. And you also have some constraints. So these are basically the binary encoded version of the same problem. So now there are 2 basically issues with this formulation. The first issue is that constraint number 2 and 3 are still nonlinear. And the second issue is that we didn't solve the case of multiplication, because this objective value that we have here is nothing but the binary encoded version of the same objective value that we had before. So I promise you that I will resolve that case of multiplication, but I ended up just generating a new formulation for the same problem, but a little bit more complicated. So let's see how we can resolve these issues. So nonlinearity can be actually resolved quite easily. So we had 2 sources of nonlinearity. Constraint number 2 was nonlinear, if you remember. And in order to linearize this constraint, we can actually do it very easily, because y hats are binary variables. So we can introduce a new variable ui prime, and we can use the McCormick envelopes in order to linearize this constraint. So we replace that binary product by this ui prime, and then we add these 3 constraints. Constraint number 3 was also nonlinear. For this constraint, we don't need to introduce any new variable. The nonlinearity source is the flooring function, and because v and c are actually integer values, you can actually easily linearize it by by replacing this floor function to a linear constraint. So so basically, constraint 2 and 3 can be linearized easily. Now that we linearize constraint 2 and 3, I need to tell you how we basically now have the binary encoded version of our original problem is nothing but an integer linear program. So I need to tell you how we can actually solve this integer linear program. And in order to solve this integer linear program, one way is to basically solve that integer linear program directly. I call that approach one-shot search mechanism. And so that basically means that if you solve this integer linear program, and these are the bits of your objective value, so these are the bits of your objective value. If you solve this problem, you will obtain the values of all bits at the same time. And as I said, this approach will not resolve the curse of multiplication because the objective value may remain the same. Actually, will remain the same. So in order to resolve the case of the multiplication, I need to find a different way to solve the problem. And if you think about it, in this case, bit number 6 is actually the most significant bit. So if you're maximizing this bit, you prefer this bit to take the value of 1. And you cannot sacrifice the value of bit number 6 to improve the value of bit number 5. So you always need to first find the value of bit number 6, earlier than bit number 5, 4, and so on and so forth. And if you're minimizing, the same thing, you're trying to force the value of bit number 6 to 0. So that gives us an indication that we don't need to solve the problem using the one-shot approach. We can solve the problem bit by bit. So that means that in each iteration, I only try to find the value of 1 bit. So I start from the most significant bit. I try to optimize that bit. So I try to find out whether or not the value of this is 0 or 1. I fix it, go to the next bit. Fix it, go to the next bit, and so on and so forth. Okay, so now you can see that using the bitwise approach, I need to solve more number of single objective IPs. But the good news is that the objective functions disappear. The objective function of the original problem disappears. I don't need to know what is the optimal objective value. I try to find out the value of its bits one by one. Okay, so that's what I do. And that will resolve the case of multiplication completely. So, so here are basically a summary of the search mechanism. You have one-shot approach and bitwise approach that I want to explain in this I explain in this sort of talk. But I want to tell you that there are tons of other search mechanisms that you can develop, and we have personally not yet had a chance to explore. These are future research direction. I call them batch-wise approaches, that they lie between one-shot and bitwise. So basically, it means that if you have 6 bits, instead of going bit by bit or one-shot, you can go batch by batch, from the most significant batch to the least significant batch. For example, I can start from batch dispatch, and dispatch tries to find the value of bit number 5 and 6 together. And in order to do that, you only need to optimize this function. Since bit number 6 is significantly more important bit number 5, you need to give an exponential sort of coefficient to bit number 6, because you cannot sacrifice any value of bit number 6 for improving the bit value bit number 5. So this is the objective function. You solve this thing, and you will actually get the value of bit 5 and 6 together. Now I can go to the next batch. This batch maybe have 4 bits together, let's say, and then in this batch you try to optimize this problem, and bit number 4 should have a significantly larger coefficient than the other bits. And bit number 3 should have a much larger coefficient than bit number 1 and 2, and so on and so forth. So you have an exponential trend here. So once you solve this optimization problem, you have the values of all 4 bits together, you fix them, and you solve the last one, and the last one is just 1 bit. So you solve this thing. So using this batch-wise approach, you may solve a less number of IPs compared to the bitwise. So some remarks that I want to mention. So if you are solving the one-shot approach, you're only solving one single objective integer linear programs. If you're solving the bitwise approach, you solve more number of IPs, and this number of IPs depends on number of bits required to denote your optimal objective value. So you solve precisely that number of bits. You can also find one nice thing about the bitwise search mechanism is that you can find a global primal bound for your problem at each iteration. So that basically means that you can, if you have, let's say, if you're here and you have calculated the value of bit number 6, 5, and 4 so far, so that means that you already have a solution in the memory for the other bits that you have not yet optimized. And those values may not be optimal, right? But because you have that solution, you can actually compute a primal bound for your problem. If you want, you can compute a dual bound for your problem as well. Consider the same problem. If I want to compute a dual bound, all I need to do, I need to consider the value of the bits that I have not yet explored. I need to put them to their ideal case. For example, if I'm maximizing, I put the value of bit number 0 to 3 to the ideal values, and the ideal value is 1. So I create a basically imaginary solution, and that solution gives me the dual bound of 95. In the bitwise search mechanism, you can sometimes skip an optimization problem if you like. This is interesting. For example, if you are here and you have calculated the value of bit number 4, and you want to now go and explore bit number 3, you actually don't need to explore bit number 3, because in the memory you have a solution, and that solution already showing you that the ideal value of bit number 3 is satisfied. Ideal value is 1. So you don't need to search bit number 3. You also don't need to search bit number 2 as well, because you already have a solution that bit number 2 is getting its ideal value. So I skip bit number 3 and 2. I immediately go to bit number 1 and calculate that thing. So I skip to optimization problem. You can also develop some sort of cuts for your problem, and the cuts are actually quite helpful. For example, consider this example again. You're here in the red sort of square, and you haven't yet explored bit number 0 to 3. So I look at the solution that I have in the memory. It turns out that bit number 3, bit number 0, and bit number 1, they have not yet received their ideal values. So I'm going to add cuts to the problem and say that, look, at least one of them should be 1. Because if one of them is not 1, then the solution that originally I already have in the memory must be optimal. So I add this cut to the memory, to the problem, and I solve that optimization problem. If the optimization problem turns out to be infeasible, I don't need to search any other value of any of the bits, because the solution that I currently have must be optimal. You can change this cut that I mentioned slightly to get a different cut. I call it p-cut. The p-cut is similar to the previous cut. The only difference is that I first check in the solution and look at the bits that are not yet explored to find out what is the most significant bit that its value is 1. In this case, bit number 1 is the most significant bit that I have not yet explored and has the value 1. So I look at the bits that are larger than that and they are not yet explored, and I add my cut based on that. So basically, I add this cut that the value of bit number 2 and 1, at least one of them should be greater than 1. So if I add this cut to the problem, when I'm exploring bit number 3, the problem may become infeasible, because there may be no way that these two values to be 1. If the problem is infeasible, so I can immediately skip bit number 2, because I know that there's no way to make the value of bit number 2 equal to 0. So in that case, I don't need to explore bit number 2 and 3. Both of them should get the value of 1. And I can immediately go to bit number 1. And you can, and bit number 1 has the value of 1 here. So that means that it has its ideal value. So that means that I even don't need to explore bit number 1 because it has its ideal value. So I can skip to optimization problem and immediately go to bit number 0. So now I hope that you, by now you understand that initial feasible solution can be actually quite helpful, or having any feasible solution quite helpful in getting rid of some of the optimization problems. So if you have if you have an initial sort of feasible solution, we can skip some of the optimization problems. For example, if you have these solutions in the memory and you're minimizing, so that means that you don't need to explore bit number 6, 5, and 4 together, because 0 is the ideal value when you're dealing with the minimization problem. So I can skip all of those things and immediately go to bit number 3. How to calculate a warm start solution? You can use any techniques that you like, 2 of which are explained here. So we propose to use a min-min operation. So you're minimizing the minimum value of y among all the y values. So you calculate either this directly or you can do it indirectly. So that means that you calculate these y values independently and then you pick the minimum of them. And by doing that, you can get an initial feasible solution, and maybe that initial feasible solution helps you to get rid of some of the optimization problems. One other thing that I wanted to mention is that so far I explained to you that if you have a binary encoded reformulation, there are two search mechanism that you can use. But I haven't yet told you how you can actually write down the binary encoded reformulation for the cases that you have more than 2 terms in the objective function. If you have more than 2 terms in the objective function in general, one way to write down your binary encoded reformulation is the nested reformulation. The nested reformulation basically means that you calculate the multiplication of y1 and y2 first. The outcome of that will be multiplied by y3. The outcome of that will be multiplied by y4, and so on and so forth. So you're going to have p minus 1 sequential binary multiplication. So you can write down the formulation of that thing easily. So I'm not going to go through it, but you have all the principles that I explained previously. You binary encode y values. You linearize the bilinear terms. Some of each column you should represent by value of v. You need to calculate the carried values, and finally you can get the value of bits. One interesting thing about the nested reformulation is that because you only have p minus 1 sequential binary products, so when you're doing linearization, you're still going to face only bilinear terms that you need to linearize. Okay, so keep that in mind, please. Another way to deal with the problem is that if you don't want to use the nested reformulation, you can use altogether reformulation. Altogether reformulation is this that I have written here. So that basically means that you don't do the binary products. You try to calculate the value of the product together, just in one shot. Okay. So how can you do that? Well, for doing so, you can use the generalized fast Fourier transform based on multiplication of integers. For example, if you have 3 values, y1, y2, y3, and they are taking the value of 7, you can binary encode the value of 7, which is this value here with 8 bits. Let's say you can binary encode the value of y1 and y2 as well. Once you calculate that thing, you can now multiply 3 terms together in order to create this middle section value here. For example, if you want to calculate this value here, this is a multiplication of these 3 terms. So once you, so the only difference between this and the binary product is that in this case, I need to multiply 3 items together, right? 3 binary values together. Previously in binary product, you only multiply 2 of them together. So the rest is going to be similar. So you just calculate the value of each column, carried values, and you compute the value of the bits. So this is the formulation for that. So basically the same principles, binary encoding the value of y's, linearizing multilinear terms here, sum of each column, and carried values and bit values. So here's the big difference between the altogether formulation and nested formulation. In the altogether formulation, you need to linearize multilinear terms, because remember, if you have 3, let's say values y1, y2, y3, this product, this summation of each column, is basically this number here are the product of 3 numbers. So they're going to be, so the linearization becomes tough because you multiply p products together. Okay, so long story short, you have 2 family of reformulations that you can use altogether or nested. These are the 2 things that we came up with, but you can also do lots of other future research direction and come up with hybrid methods. These are the methods that we personally have not yet explored, but we know they exist. Basically, in order to create a hybrid method, you can partition the index set of 1 to p into an arbitrary number of non-empty batches, b1 to bk. Then you can apply altogether reformulation to each batch individually to calculate Z1 to Zk, and then you can apply the necessary reformulation to Z1 and Zk. So you basically put together this nested and all together, and you can get a value here. You can have that thing. And then so here are just final remarks that I wanted to mention. And here we have if L represents the maximum number of bits required to encode any Y values, then the size of your multiplicative program is, and if the size of your multiplicative program is polynomial bounded, the nested formulation remain polynomially bounded. However, altogether formulation is going to be exponential because, unfortunately, linearizing that multilinear term is not an easy task, right? So you need more decision variables. So in summary, this is a proposed sort of framework, proposed family of solution methods. You can have multiple ways to reformulate the problem, multiple ways to develop a search mechanism, and you can have many ways to basically develop enhancement techniques. So we apply that thing into solving a large sort of instance with 15 terms of multiplication. So note that the true solution approach in order to deal with the curse of multiplication is to use the nested reformulation, because that's polynomially bounded, and bitwise approach, because that will resolve the case of multiplication. So we try to compare our approach with the Groby optimizer in both minimization and maximization. You see, this is the objective value that the optimal objective value found by our approach. Groby, after less than 1 second, it runs into numerical issues because P is large, and you can see that it reported a solution that is not optimal. If you increase the value of P, it becomes even worse. Groby reports infeasibility, while the problem is actually has a very, very large objective value in both minimization and maximization. And so that's how long it takes to solve such a problem. So our approach can solve the case of multiplication. If you have a large number of P's, you can actually use it. So then we ask this question whether or not our approach is going to be useful for the small values of the P's. And then and we were able to make some conclusion regarding that too. So here, N represent the nested, O represent the one-shot, B represent the bitwise, and F represent the F-cut. So I'm just going to show you some just results, and I'm going to end my talk now. Basically, for the case of P equal to 2, it turns out that if you want to use our approach, not surprisingly, nested optimizer with the one-shot approach is going to give you the best solution time. But when you're solving and warm start sort of a strategy that I explained also are going to be effective when in order to decrease time. And however, if P is small, in the case of maximization, second order programming solver of SOCP of Groby is always the best. So you cannot compete with that. For the case of minimization, however, using our approach is also beneficial when the P is equal to P, and you can see that it outperforms the Groby non-convex solver. So in summary, here's a multiplicative program, maximization for small values of P. We have nothing. You cannot use our approach; it's not efficient. For the minimization case, our approach is going to be good, even for small values of P. And if you have continuous variables, and you want to use our approach, you need to somehow transform your decision variables into integer values. So that means that you need to consider a certain precision level, and you multiply each decision variable by that 10 to the power of 2 or 10 to the power of 4, and you assume that your Y values are actually integer, and you can apply the same technique. So thank you very much. And if you want to look at the reference, please have a look at this paper.